Good morning, everyone. I hope you're enjoying the cool weather. We have crisp weather in the morning, and then in the afternoon, it's nice and temperate, like we live in Florida. So I guess it's nice to really live in Texas because we do suffer from some of Mother Nature, but we are a little bit protected. Maybe not as I guess when we compare ourselves to other places, we don't suffer earthquakes and we don't usually have too many tornadoes. So we're in a pretty good place. Of course, if you live in Florida, where you just have beautiful weather all the time, you have to suffer a lot more hurricanes and bad weather. So I guess we get a really nice mix of weather here, unless it starts to rain a lot. So maybe in the Houston area, we found the right balance of safety and nice weather. So I hope you're enjoying that. I know I like it to run in the morning when it's nice and cool. It's a nice change. Now, just remember we have our test coming up, and I'm going to want you to just submit a PDF of your work and basically just do a scan of that. I'm sure you probably had to do this for other classes, and there are lots of free apps that are useful for PDF scan. I use the Adobe Scan, but I have an Adobe account, and so that might require like a trial period or some type of fee, which you may not be interested in doing. I mean, of course, it's a very nice little app I use on my phone to do all kinds of scanning, but they're free apps on the Google Store or the iPhone Store, so you can find something to upload. So basically, once you're done, just do a PDF scan of your work and submit it on the Turnitin where I have the test three work. This is just basically a formality. It doesn't really affect anything. I just want to see that you're working things out. And again, the only problem that we would incur from this would be that you just didn't submit anything. I just want to see that you're working things out. And I know each of you have your own methods, and some of you write a lot, some of you don't write much at all, I'm sure. But I just want to be able to see that. I think that just gives me a better feeling about what you're doing, and since you're now accustomed to what I'm doing, you know what I expect of you. So that'll be available on Thursday in the same time window that you had for the previous two tests. So keep that in mind and have everything ready to go when you sit down to take your test, and do some planning. Again, I give you plenty of time so that there will be some ease and lower stress. The main thing is low stress, and that's what I want for you. Okay, so what are we doing today? Well, we're going to finish up the triangles, the law of cosines, and Heron's formula, which is a corollary of that. And then we're going to talk about some basic identities, introduce the cofunction identities, and do some work with just proving identities using the trig identities that you already know. So you'll find the first section of chapter 7 to be very straightforward and kind of reaffirming, and maybe a nice break from all the tedious arithmetic that we have to do with the unit circle. So that'll be good. And then of course, once we leave 7.1, we move into more identities, and then we conclude with the trigonometric equations, which will take into account all of this wonderful arithmetic that we've introduced and keep us on the straight and narrow, so to speak. Uh, I've made a big point to focus on the arithmetic of the unit circle, the pluses and the minuses, the reference numbers, the reference angles, so that that will pay off when we actually solve equations. I mean, we don't want to solve an equation like we have blinders on. That's not good. I mean, oh, I'll keep my fingers crossed I get the right answer. I want you to have more confidence than that. So let me go ahead and share my screen and we'll get started. Now, the law of cosines is actually just another rendering of the triangle that is similar to that of the law of sines, but again, it has a little bit different focus. Um, what we find, and I'm sure you remember this in your high school geometry class. Let me move Professor Ryan over a little bit. You have all kinds of interesting theorems And sometimes you're thinking, well, that's really interesting. When am I ever going to use that? And maybe there are lots of things that you did in your geometry class that you haven't had occasion to reuse. But we certainly know things that are very, very important that get frequent use in pre-calc and the calculus sequence. So when we were doing the law of sines, we saw that we could solve angle side angle, which was again a fixed triangle, and then side side angle, which was the ambiguous case. And so we thought, that's not the best thing, but again, that utilizes the sine equation, Professor Ron's lemma. So that wasn't a perfect world, but we knew how to negotiate it, and that's a good thing. Now, what's left? Well, what's left is the side, 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 and that's actually a fixed triangle from your high school geometry, and then the side angle side. Again, another fixed triangle. So even if we have a sine equation, it's only going to provide us with what we need. And then, of course, we figure out what kind of angle we're going to have, and then we'll be done. So again, these are clear-cut cases. The geometry here says that if you have these parameters for a triangle, then you have completely specified the triangle. So there's no ambiguity like we have in the ambiguous case. But this was no good with the law of sines. We could not get things started with the law of sines. We needed something new. So I'll just say the present theorem will solve these cases. And I say will solve, it just basically gets the ball rolling. Will solve these cases. We have to have some way of getting an initial computation. And let me just focus on a couple of things here. Make sure that all of your calculations are exact. Do not round, as WebAssign might say, for a particular component of the triangle, and then use a rounded figure in your computations. Ladies and gentlemen, I know you know that's not correct. That introduces inaccuracy into your calculations. I never do that. And I don't know why you are compelled to do it. Please don't do that. Always make sure you write exact calculations. And then if you have a number that you have with your Google calculator, then use that number in a subsequent calculation that's not rounded. That way you keep all of your mathematics exact. You cannot expect to have good, clean mathematics when you round indiscriminately and then use those rounded figures in your computations as if you think that's going to give you the correct answer. So please don't do that. And if you feel like I'm preaching, well, I'm not going to say I'm sorry. I want you to know this. I want you to do good mathematics and keep everything nice and clean. So how do we start with this? Here's the theorem. We start with a generic triangle. So consider, the lazy triangle that we write. Consider the generic triangle. Now I use you all sometimes as my congregation, and I'm not saying that you do it. I'm just saying if you're not, then share that with your friends who may not be as wise. I use all the messages and emails I get through WebAssign to kind of take a snapshot of how students are doing. So just be sure to pass along the good ideas. Now, what I want to do in this case is provide some type of explanation for the obtuse case, and then we can look at a corollary of this particular theorem. Now, one thing we often call this, we call this the generalized Pythagorean theorem. So when I write the equations, they're gonna look very familiar. Generalized Pythagorean theorem. So when we think about how things are related, the Pythagorean theorem is a linchpin for what we do. And so we're gonna make it even better. So the first equation that we're going to have, and these are all going to be equivalent. So I'm not saying that there are three results. I'm just saying that they may come in different packages. So we might have a squared, where this is the a, the b, and the c from the generic triangle, is b squared plus c squared minus 2ab cosine of the angle C. Okay, so there's nothing special about A, B, and C in this configuration. Maybe we focus on angle B and its opposite side. So let's write that down. These are all symmetric. B squared equals A squared plus C squared. So we just permute things. Minus 2AC cosine B. So this is a really easy way to remember this. The side here, lowercase b, and the opposite angle goes with the cosine. So that's easy to remember. And then of course the AC here, we see the AC in the product here. So it makes it simple to remember. And then the third case would be C squared equals A squared plus B squared minus 2AB. And of course, I just refuted what I said with the angles. That's an A there. See, good old mathematics, it tells us what to write. So here with the A squared, I need to pair that with the angle A, the opposite side. B needs to be paired with its opposite angle, so to speak, and C likewise. So again, if if you write it incorrectly or have a typo, boom, it's like, boom, do this correctly, Professor Ron. So this is good. So all of these are equivalent. So this is really what brings everything together. The side, and the side angle side are actually able to be dealt with this kind of configuration. So again, this is kind of the missing piece of the puzzle that we needed before. So what I want to do is look at the obtuse triangle, and then if you want to later on look at the acute triangle, and you can follow the method I'm doing here. What I want us to do is get into some algebra that will help us with identities, and we haven't been doing a crazy amount of algebra, so I want to put some more of that into the lecture. So let's draw our X and Y axis. Now, when we look at this, what I want to do, and I've kind of shifted this over, but that's all right. We'll have plenty of room. I want to utilize this as my x-axis, of course, and this is my y-axis, and I want to use the origin as one of the vertices of the triangle. So when I coordinatize everything, this is just at the origin. So let's go ahead and mark this off. Let's just go ahead and mark this point as A, vertex A, angle A, with X and Y coordinate 0, 0. And then if you like, we can put C over here and B over here. So C, well, let me just go ahead and draw these, and then we'll use the generic setup. So B, we'll have to do a little bit of work to figure out those coordinates, but not much. This one will be clearly easy. So let's go ahead and connect these points. So here, notice this is B, so this is side B here. This will be C, and so because we have this particular side of the triangle along the x-axis, this would just be the coordinate B, comma 0. So again, that makes this coordinate easy if we go ahead and place one side of the triangle on the x-axis with one vertex at the origin. So that simplifies the coordinates. And now, of course, here's A. So the opposite side here, we have A. And then we've got C here. So this is lowercase c. So that triangle is labeled at least as much as we can do initially. Now, in order to actually do this, we did this with the area formula with the sine. We're going to drop a perpendicular. So now we can actually think about, okay, now look, we have a large right triangle here. So that's going to be helpful. So we're actually going to use the standard Pythagorean theorem to generalize it. So again, that's okay. We're using a result to extend a result. So that's not circular reasoning. That's actually pretty good. So we're going to make the Pythagorean theorem even better. So now, in order to move this forward, first we see that this is angle A. And so it is a second quadrant angle. So the angle here is just the supplement of that, and that gives us the reference angle by definition. So this is just pi minus A. That's the reference angle for this angle here, A. So this is a reference angle. I'll put a little arc there just so you see that's the reference angle. So I'll just note A hat, so to speak, is pi minus A. So we're going to use that when we can determine these coordinates. So that's just like what we did with the sine function. Now, of course, I'll just go ahead and mark this as a generic x, so we can use that as a variable placeholder. And I'll mark this as a generic y as a variable placeholder. So now when we look at this and we think about what we're doing here, we want to say, okay, well, we can use this reference angle to make this computation here and then translate into the angle A. So now what we see is that thinking of this as cosine adjacent over hypotenuse, we see that cosine of the reference angle, again, this is the reference angle, but in the second quadrant, the cosine is negative. So we have to go backwards and affix the negative sign to the cosine of A. So this will be the negative cosine of A. Normally we go cosine of A and then move to the reference, but now we're actually going backwards. So we transfer the negative this way. So these are equal. And then the cosine of A in terms of the triangles will be adjacent over hypotenuse. So this is x over c. So very simple, but very important using the arithmetic of the unit circle. And so now we see x equals negative c times cosine of A. So that gives the x coordinate of the B vertex. And now we can do the same for the sine. So we'll do sine of the reference angle. Okay, now remember the sine is the y, which in the second quadrant is still positive. So this actually equals sine of A. So there's no shift in sine like we had with cosine. The sine function is very interesting. It's an odd function. Odd in the sense that algebraically odd, but it is odd in the sense of how you solve equations. We've already seen the arithmetic that results from that, especially based on how we define the inverse sine function. So this will be opposite over hypotenuse. So this is y over c. So then, of course, we can solve for y by cross multiplying. So y equals c times sine A. So now we can go to coordinate or vertex B and write in its coordinates. So we have negative C cosine A, comma, C sine A. Now it didn't really matter how I put the vertices here. I mean, I could have permuted the A, B, and C. It doesn't matter. We're going to end up with what looks like this number 1 because we've got the hypotenuse there. But it doesn't matter. These are all equivalent. So if you draw your triangle that looks like this for the acute case, it's still the same. So try that if you like. Now, like I said before, this larger triangle is a right triangle. So we need to use the Pythagorean theorem. So we know that the hypotenuse squared is simply the sum of the squares of the legs. So we have A squared. Now, of course, we have this in 2 pieces. Y, we know, is C sine A. So we have C sine A quantity squared. And then we need this leg, but we know that it's the distance here, B, plus the distance here, which is negative C cosine A. So we have plus, I guess we can do the B first, B minus C cosine A quantity squared. So the distance from here to here is just B minus C cosine A right there. And again, the arithmetic is essential here. Without it, we're sunk. If you ignore the arithmetic of the unit circle, then you can not expect your work to be correct. That's why I'm teaching you the way I do. I want you to get the calculus and know what you're doing and have confidence and not just say, well, I was never any good at trig. Don't be in that position. That's no good. That's not what you want. So be very vigilant about taking care of the arithmetic. And now you see it's all just going to fall out in the wash. So we have A squared. And of course, if we square this, we get C squared sine squared A. And now we can square the binomial. So we're going to get B squared. And then take the product of these two and hit it with a 2. So that gives us minus 2bc cosine A. And then square the last term of the binomial. This will give us plus c squared cosine squared A. Now, I've had a lot of questions about this notation. Remember, when we write cosine squared A, that is shorthand for the square of cosine A. So we could write this every time, but that's a bit cumbersome. So we adopt this shorthand notation. I know you know this, but it never hurts to review it. But now, of course, we could also take the cosine of the square of A, but no, that's not equal to this. So don't make the mistake of confusing these two. When we have the square here as a superscript of COS, that means the square of cosine A, the shorthand. This just means what it means, and that's clearly not equal to that. So you know, unless if you're going to look at it with simple values of A, you know, you can have some equality, but in general, this is not true. So be careful with the notation. I know you know it, but it never hurts to review what all the symbols mean. So now we look at this and say, well, let's bring the computation down here. We have A squared, and we've got a C squared here and a C squared here, so we can factor. So we have C squared sine squared A plus cosine squared A. So that takes care of these, and then these are fixed. So now we have a squared. Well, if we want to put things in alphabetical order, notice the sine squared plus the cosine squared is just a fundamental identity. This equals 1. So if we write things like we have here, we get b squared plus c squared minus the product term, 2bc cosine A. So if you write something incorrectly, you see that the math corrects you. So what I wanted to show you here is that we use a similar argument for the obtuse case that we did for the area of the triangle using the sine function. And what we're actually doing here, even though the Greeks came up with these results with different means, they were very smart, but they didn't use this type of analytic geometry. When we take geometric objects and we coordinatize them, I couldn't say that this morning for some reason until like the third time. I don't know, it must have been too early. I said, I finally did it. Professor Ron could say coordinatize. So the thing, oh, and I was trying to say a noun, which I don't even know is a word, coordinatization. I think that's just something I made up, but whatever. I should check it. So when you look here, you're thinking, okay, we use analytic geometry to combine the algebra of the plane with the geometry of the triangle. And so that is something that Descartes actually investigated. Rene Descartes was, as you know, a philosopher and mathematician, and we owe all of his genius to the Cartesian plane. So we have to have, I guess, come up with some other alternative to this, but I could never see that it would be an improvement on this. It's like someone coming up with an improvement on calculus. It's just not going to happen. We're lucky that we had some smart people in our past to lay the groundwork for us. So now we see that we do have the generalization of the Pythagorean theorem. This is basically the Pythagorean theorem. And of course, if A is a right angle, this term is 0 because cosine of 90 degrees or cosine of pi over 2 is identically 0. So this reduces to the Pythagorean theorem. So this indeed is a generalization of it. So again, it must be a pretty good result because it makes this theorem even better. Okay, so the use of this is similar to the law of sines, but what I want to do right now is to take an opportunity to push this into the realm of triangle area. When you do geometry, you often think about, okay, well, we have a formula that uses these parameters. We have a formula that uses these parameters. What if we have a case where all we know about the triangle is like some of the problems we did with the inverse trig functions? That is, we know all of the sides. And you're thinking, well, Professor Ron, we can use inverse trig functions to find the angles. You showed us how to do that. But say, for instance, you don't have the inverse trig functions and you just simply want to possibly find the area of the triangle just knowing the lengths of the sides. Is that possible? And it is possible, but you may not have seen this before. And this is something that's very interesting because it's a direct result of the law of cosines. And for all you history buffs, you know the name of Heron. So this is Heron's formula. I thought it's interesting to learn new things. You're thinking, you know, is this another useless formula? Well, what we're going to find with this is that it's actually a very useful calculation or useful theorem to have. Not everything in mathematics has utility. It was thought that number theory was just fun for math people, for genius people, for nerdy people. You just do number theory. Well, little did the mathematicians of the day, well, the mathematicians knew better, but the general population just kind of looked at number theory as the playground for mathematicians and said, oh, okay, well, you just do your number theory and have a good time. Now we see that we live in a computer science world and technology where number theory has basically taken over. So you have no idea. I mean, when scientists say that physics is the mother of all science, well, good for them. But there would be no science without mathematics, because mathematics is indeed the language of any STEM discipline. And without it, we have nothing. So the next time someone says, oh, yes, physics is what it's all about, you might just say, okay, well, how much physics could you do without the mathematics? How much chemistry could you do without mathematics? Biology, engineering. Those of you that want to be chemical engineers, you're going to have to learn some organic chemistry, and you'll enjoy that, and inorganic too. And that will be a lot of mechanisms with the chemistry side, but you'll have to understand the physical aspects of these particular compounds, which will require calculus and analysis. So you're stuck too. And if you want to be an electrical engineer, then you're going to have to take more math than any discipline in engineering. So you're stuck with that. But the rewards of being a double E engineer or just a double E are remarkable. You can write your ticket. You can live anywhere in the world. So just remember that if you want to be an electrical engineer. Now, of course, students that like electrical engineering think, well, I'll just be a computer engineer and work for Google. That'll work too. So what do we need for Heron's formula? So we've got this generic triangle. We need a new object, and it's called the semiperimeter. Semiperimeter. Because you're thinking we're going to have a formula that only has A, B, and C in it, or some form or some combination of that. And this is what Heron came up with in his own way. We define, and I'm sorry we use an S here, you can change it to another letter. That's not arc length. It's just going to be the sum of the lengths of the triangle legs divided by 2. So this is just a particular object that actually appears in the calculations, or we make it so that this appears, and this simplifies the statement of Heron's formula. So this is what we're going to call the semiperimeter. So again, it's just like taking the perimeter of a polygon, but the semi part comes from dividing by 2. So again, these are the lengths of the side of the generic triangle. So we could have something like this. So we've got the opposite side C, we've got the angle C, and the included. Basically the sides with the included angle. So we're going to start with our old friend, the sine formula, and move this forward. And then, of course, what did I say? This is a corollary of the what? Law of cosine. So somewhere we're going to replace cosine of some angle with you know, A's, B's, and C's in order to write this completely in terms of the lengths of the sides. So that's where we're headed. So now what we're going to do is let A be the area of the triangle. And because you're thinking that we've got all of these squares hanging out, and you're thinking, you know, let's make this a simple calculation, it will be much easier on everyone concerned if we consider the square of the area. So here's what we're going to do. We're going to consider this. And then at the very end, we'll take a principal square root. So consider A squared. Now we go to the formula that we have here for the area of the triangle, which again, we could pick any vertex you want. We'll just pick this one, doesn't matter. So we'll have what? 1/2 A times B, in this case, times the sine of the included angle. Okay, so we're thinking, all right, well, here we go. So what does this equal? So we've got the square of 1/2, which is 1/4, and we have a squared, b squared, and then we have sine squared of the angle C. So sine of C, quantity squared. Now, when we look at this, we're thinking, okay, well, Heron's formula has to only include things like this. This is really not what we want, and we want to use the law of cosines. So we can rewrite this using the cosine, using the fundamental identity, so we can go directly to the law of cosines and see what that tells us. So what does this give us? So this will be 1/4 a squared b squared, and then we'll replace the square of sine C with 1 minus the square of cosine C using the fundamental identity right here. So now you're thinking, all right, well, okay, how do I want to do this at this point, Professor Ron? I mean, if that's the square, I don't really have the square of cosine C in the law of cosines. I just have the first power. Okay, so with that in mind, we might think to factor this. This is a difference of two squares. So this is 1/4 a squared b squared. Then this will be 1 minus cosine C times 1 plus cosine C. So these types of algebraic manipulations we'll have to do when we prove identity. So this is why I want to go through these calculations, because they're very important. Now you're thinking, all right, now I see that we've got the cosine there. So we need a little side calculation here. So let's do that. And I'll just right here, just say side calculation. I would write it over here, but I don't have enough room. I didn't move things. I could have moved this down and put it over here. So sorry, I have to kind of interrupt this, but you'll forgive me. So side calculation. So what do we know? Well, we know the cosine C. Let's see, where's that formula that we just derived? Right here. So let's use number 3. So we know C squared equals A squared plus B squared minus 2AB cosine C. Now, when we look at that, we think, okay, well, we need cosine C, so let's transpose this and transpose the C squared. So this will give us 2AB cosine C equals A squared plus B squared minus C squared. And now we can actually solve for cosine C if we divide by 2AB. So let me get some focus there. Yeah, that looks better. Oh, I just lost my picture. Sorry. I've got a touch screen. Sometimes I use it and then I hit the wrong thing. Ugh. Okay, so now let's divide by 2AB. So cosine C equals A squared plus B squared minus C squared. And it looks a little light. Let me take the lightness down just a little bit. There we go. That's a little bit better. Hopefully you can see everything. Divided by 2AB. So this is an expression for the cosine. And that's good because this is going to allow us to get rid of the A squared, B squared eventually up here with these things in the denominator. So now we'll do a substitution. So what do we get? 1/4 A squared, B squared. And then we get 1 minus this guy, A squared plus B squared minus C squared divided by 2AB. And then we get 1 plus a squared plus b squared minus c squared divided by 2ab. So it's like you're back in college algebra, or well, maybe the beginning of this class. So now we're thinking, okay, this is looking a lot better. You know, we've got A's, B's, and C's. That's it. So what we want to do in this particular case, let me put this up here so you can see it. We want to go ahead and get a common denominator. So we have 1/4 a squared b squared. So we have 2ab, which will, ab is going to absorb, and the 2 will just multiply there. So this will give us 2ab, distribute the negative sign, minus a squared minus b squared, and then of course minus minus plus c squared. And now here we have 2ab, common denominator again, 2ab. Now this is easy, we just have a bunch of pluses, a squared plus b squared minus c squared. Now notice that the ab times the ab is just a squared b squared, which will absorb that. So those terms will be gone. And then the 2 times the 2 will multiply the 4 to give us a 16. So now this gives us 16. And then we can make some comments here. Notice we have perfect squares here. This is the negative of a minus b quantity squared. Because when we expand that, we get an a squared minus 2ab plus b squared with the negative. That gives us all of these guys right here. And then here, this is another perfect square. This is just a plus b quantity squared. So when we square that, we get a squared plus b squared plus 2ab. So we just need the negative here so we get the signs correct. And here we don't need any sign change because we just got all pluses. So that's good too. So now we're going to have differences of 2 squares again, which we can further simplify by factoring. So now the a squared, b squared are absorbed, and we get 4 times 4, which is 1/16. And this leaves us with, well, we'll just write the c squared first, minus a minus b quantity squared. And then here we have a plus b quantity squared minus c squared. So now, just like we had here, we have a difference of squares here and here. So we're going to factor just like we did here. So now this gives us 1/16. So this will give us what? C minus a minus b. So c minus a minus b times c plus a minus b. Do the same here. This will be a plus b minus c times a plus b plus c. So now you're seeing why the semi-perimeter was basically defined, because we're seeing part of it right here. That is, there's the semi-perimeter, and we've got basically this here, it's times 2. Now what we want to do is just clean this up and see how we can force the s into all of these factors. So 1/16. So we got a minus a, but minus minus gives us a plus b. So that'll be a b plus c minus a. And then here we have an a plus c minus a b. Well, that's ready to go, a plus b minus c. It sounds the same when you say the a, whatever, they sound the same. I'm sorry, try to make it sound different. And a plus b plus c, that's fixed. So in order to basically present or to, what we want to do is rewrite these factors so we can introduce S. That means we need an extra copy of A here, we need an extra copy of B here, and we need an extra copy of C here. So how do we do it? We add and subtract each of those letters to basically be adding 0. So now this gives us equals 1 over 16 A plus B plus C minus 2A. Then we get A plus B plus C minus 2B. And then we get A plus B plus C minus 2C. And then, of course, the A plus B plus C is fixed. So now you're like, oh, okay, I get it. And now what we can do to finish this off, and then we'll do an example of this, we see that we've got 4 copies of 2 here. So if we bring the 2 under here, a 2 here, a 2 here, and a 2 here, which gives us the 16, we'll get the semi-parameter, and the 2 here will absorb. So now what do we get? We get A plus B plus C over 2 minus A. We get A plus B plus C divided by 2 minus B. We get A plus B plus C over 2 minus C. And then here we just get A plus B plus C divided by 2. So we basically take the 16, 2, 2, 2, 2. And so now you're thinking, okay, we go back up to the top and say we've just defined the semi-parameter 4 times. So now this is S minus A, S minus B, S minus C, and S. So let's put the S at front. So S minus A, S minus B, and S minus C. So now when you think about this, it's kind of miraculous. We now have a formula for A squared. And so at this point, we're thinking, okay, is this good enough? Well, I will tell you this is good enough. This is like crazy simple compared to what we started with. So now take positive square root. So this gives us A is the principal square root of S times S minus A times S minus B times S minus C. So one nice thing about this is just like the law of cosines and the law of sines. If you just indiscriminately make up a triangle like it exists, you know, you draw it and you label it and it's just nonsense, this will basically tell you that. Because if one of these factors happens to be negative, then you've defied the geometry, okay? This is a really good check. If you're doing a modeling exercise in a physics class or in an engineering class, and you know, it's like you've got to construct this model where, well, the mathematics has to agree with it because you've got to say, well, this side needs to be this length or whatever. And so this is a good check on that. So the mathematics has to agree. It's kind of interesting. We see that the marriage between the number theory and algebra and the geometry is there because they're really all the same. When we do geometric constructions, we're doing algebra. And when we study more advanced algebra, we see that the impossibility of certain constructions is due to the fact that there is an impossibility of solving an equation in algebra. So they are the same. And it was due to some of these great minds who found that connection. And one of the persons was Évariste Galois, who created the Galois theory, which I studied in graduate school. And trust me, it's amazing. It's amazing the illumination that you see. And so when we study theory of equations, all of that basically nice foundation that we have, even though you think it's maybe still somewhat awkward to do, is due to the genius of these individuals. So we don't try to solve certain equations by radicals when we know it is not possible to do. So that's why the science of numerical analysis has grown so much, because we have the fancy computers to crunch numbers. So again, always a mathematical justification behind what we do. So what I want to do now is use this formula, and then I'm going to go back and solve a triangle using the law of cosines. So let's do that example. Now, this particular example, again, is fairly simple, but it's simple because we have Heron's formula. So you'll see a lot. This is what I was talking about last class with these interesting figures that we'll be able to now analyze because we have the Heron's formula. So enjoy doing these. So we have an example. We basically have two isosceles triangles juxtaposed. So it's an interesting figure. We have something like this. Now, of course, a picture doesn't tell you anything, but if it's labeled in such a way, it does give you some ideas as to actually what it is. So we have a side of length 3, we have this side of length 3, and then we have a side of length 3 here. So this is 3, 3, and 3. And then this measurement is 1, and this measurement is 1. So now when we look at this, we have isosceles triangles. So these angles are all congruent. So you can call this triangle 1, and you can call this triangle 2. So now if we do what Webesain says, here's what Webesain says. It says compute the area of, in this case, the polygon. So what do you do when you try to compute areas of polygons? You just chop them up into triangles usually. And now we can see, and we can just say, let A be the area. Then, because these two triangles are congruent, so to speak, we can say then A equals twice the area of triangle 1. Right there. So we're thinking, okay, we'll find the area of this triangle and just double it. But now we're not gonna do the approach that we would do with the included angle. We could solve for an included angle, but we want to go ahead and use the powerful result, Heron's formula. So just remember, there's never an exact way to do anything. I mean, you can choose whatever method you want. I mean, the results will be the same. But here, I just want to use the Heron's formula. So now notice, we can say A equals 3, B equals 3, and C equals 1. However you want to assign these, it doesn't matter. And so now semi-perimeter is A plus B plus C divided by 2. This just gives you a different approach. So we have 3 plus 3 plus 1 divided by 2. And that'll give us a 7 over 2. So there's our semi-perimeter. So I'm going to just do this in pieces like we're doing the quadratic formula. Maybe it's a little bit easier than trying to, do everything linearly just to check your work. And so now we got what? S minus A will just be 7/2. And of course, we'll write this with a denominator of 2. So this will be 6/2. So this will be 1/2. And then of course, S minus B, that's the same. Let's just write it down. 7/2 minus 6/2, which is 1/2. And then of course, for the C one, we have S minus C, which will be 7/2 minus 2/2, which is 5/2. So of course, this triangle exists because all of these are non-negative. I mean, let's face it, we might get a 0, and then that just means we have a line. Okay, that's not a triangle, but at least it's not, into the imaginary sense. So the triangle theorems are nice because again, they keep us correct and legal in our geometric constructions. So now we can just look at the area of triangle 1. So let's just say area of triangle 1 . And we'll just square it since we're lazy. Let's just look at the square right now. Sorry, that looks kind of bad. And so this will just be what? S times S minus A times S minus B and S minus C. So we got 7/2 times 1/2 times 1/2 times 5/2. So there's our 16, not a surprise. So we get 16 downstairs and 35 upstairs. So this implies, this implies if we take positive square roots, so area of triangle 1 will equal just the principal square root of this, which is square root of 35 divided by 4. So this implies the area of the figure is just twice that. So A, which we find to be the area of this polygon, will be 2 times the square root of 35 divided by 4, which is square root of 35 divided by 2. So again, this is exact. We always want to look for exact answers the best we can. And then of course, if WebAssign asks for an approximation, do that. Just make sure to keep all of your work as exact as you can. And then when you need an approximation, you can rely on it. Go to your Google calculator and get a nice calculus approximation. So again, we have alternatives here, but now if you want to go directly to the area of the triangle, if you know the lengths of the sides of the triangle, then you can do that using Heron's formula. And you may find this to be useful in cases where you just don't really want to deal with angles and you want to subdivide the actual polygon into triangles. And then you might say, okay, well, if I use Heron's formula, I may need to use the law of cosines, but then you want to write everything as exactly as you can and run out as many decimals as you can. So you can see that if you truncate things around too early, then you introduce lots of error into your calculation. So be careful with that. Now, I want to now back up a little bit and just go ahead and use the law of cosines. The cosine law basically proves Heron's formula. But what we want to do in this particular case is look at an example where we can actually solve a triangle by starting the process with the law of cosines. So let's look at that. So in this particular case, let's see, what do we have from the WebAssign? We've got C equals 120 degrees. Okay, that's a nice angle. That's on the unit circle. Let's see here, let me adjust this just a little bit. There we go. So it's squared off. And then we have A, which is the side opposite angle A is 24. And we have B, which is the side opposite angle B. Now this is not side angle. That's not the ambiguous case. So if you draw it, so it's sometimes good to draw it to make sure you have what you think you have. So we have C, which is the 120 angle here. And then we have the opposite side A, so we have angle A here. And then we have the opposite side of angle B, so we have angle B here. So this is side, angle, side. Big difference. Side angle is kind of a nightmare. That's the ambiguous case. So we don't have that. We have a better situation. Well, no discrimination against side angle, but in this case, we have a fixed triangle. So geometry says, geometry dictates one triangle. So the thing is that as we work with the trigonometry, we make sure that we have all of our ducks in a row and that we're actually computing what this triangle needs. Okay, so that's the important thing. But in the back of your mind, you know that this is enough to specify a unique triangle. And so we don't have to worry about the ambiguous case here. So when you look at this and you want to get the ball rolling, the first thing you say is, well, I could go ahead and get the C. And if I have the C, then I can back up and use the law of sines to get another angle, and then we're home free. So again, this does not mean that you won't use the law of sines. It just means to get the problem started, you need the law of cosines. And then, of course, you know, you're thinking, well, the law of sines is so easy to use. If there's an opportunity to use it, I'm going to take advantage of it. So that's how we look at these types of problems. So now first, we've got the C here. So we remind ourselves or recall that C squared equals A squared plus B squared minus 2AB cosine C. Just like we were using in the proof of Heron's formula. So now we'll just look at the square here, C squared. It's always easier to look at squares. Usually when we do calculus, it's easier to look at squares. So we have what, 24 squared plus 20 squared. Sometimes when the numbers are nice, we can factor things and keep that calculations cleaner if it's at all possible. Then minus 2 times what? 24 times 20. And then notice we have a cosine of 120 degrees, but that's a nice angle. So let's just go over here and remind ourselves. In this case, this is in the second quadrant. So if we have theta, well, let me not call it theta. We just call it C, what it is. So C bar is what? 180 minus 120, which is 60, the reference angle. So this implies that cosine, again, very simple calculations. I'm just taking this to the side as practice for the upcoming test, would just be the negative of cosine of 60 degrees, which we used in our theorem proof for law of cosines. So this will just be negative 1/2. Again, the arithmetic of the unit circle, or you can just say, Professor Ron, I got my unit circle right in front of me and it's negative 1/2. That works too. But if you can't do this, you come to grief. So it's good to practice this because we always have to use it. When you do calculations in the abstract, not knowing how to do this is really a nightmare. So like I said before, practice. So now notice we've got the negative 1/2 here. And the negative 1/2 will absorb the negative here, and the 2 times the 1/2 is just 1. So that's nice. So we have C squared equals 24 squared plus 20 squared plus, now the negative 2 and the negative 1/2 absorb. and we just have 24 times 20. So that was nice. That was good of WebAssign to give us a nice angle, you know, so that's, we can work with that. So now we can go ahead and do some factoring. If you like, we can just look at the 24 here out of these two. So this will give us a 24 times a 24 plus a 20 plus a 20 squared. And now, if we look at this, we've got, well, there's a 4 in here and there's a 4 in here. And then, of course, there's a 4 in each of the copies of 20. So we can do, let's see, what do we do? 4 times 6. And then we have what, 44. So there's a 4 in there, like I said. You can see the 4, it's in both of them. And then plus 4 times 5. 4 times 5. So just doing some symbolic calculation. We haven't done this in a while. And this is like what we did, excuse me. I ran, like I say, I ran this morning and good old allergies. And so we can factor the 4's here and the 4's here. So that's going to be what, 4 times 4. So 4 squared. And then let's see, that's going to be an 11 left behind in the 6. So 6 times 11. And then here we have a 5 times a 5. So that's a 25. So we have 4 squared. And we have 66 plus 25. And that's what, an 11 and a 1. So that's what, 91. 4 squared times 91. So now take positive square root. So we're seeing the law of cosines is a little bit more complicated because it tells us more. So we have C, well, the square root of 4, or 4 squared is 4, times the square root of 91. So that's the exact value for C. And then, of course, WebAssign can tell us how to approximate it. And I think they want 1 decimal when we get to that. Let me just see. I'm not really sure. I don't really care, but I think it's 1 decimal. But this is a nice, clean calculation. So we can approximate that as we need. Now, we've got the C here, and we've got angle C. And so we can now find B because we have side B. So now back to the, let's use law of sines. So law of sines. So we can say sine of C divided by C equals sine of B divided by B. So if and only if we have sine of 120 degrees divided by, well, there we go, C. It's not at the triangle, it's right down here where we calculated it. 4 times the square root of 91 equals sine B. Well, we don't know B, so that's just sine B. And the opposite side is B is 20, little b, so to speak. So if and only if, so what does this give us? Sine B is 20. Now, of course, back up here, sine of 120, that's just, remember, sine of 120, the reference angle is 60 and the sine is positive in the second quadrant. This just equals sine of 60 degrees, and we know that's square root 3 over 2, just as a little side calculation. So we have square root 3 over 2 divided by 4 times the square root of 91. So now we, well, notice here the 2, what does that give us? That gives us a 10 over 4. So 3 over 91 square root, if we just put those under the same umbrella, and then that's 5 over 2, right? So 5 over 2, 3 over 91 to the 1/2. So now we've got nice clean work. Again, if we had approximations here, we just do the approximation with the Google calculator. So at this point, we've got C, and now we can find B using our calculus approximation using the Google calculator. Now we go back up here. We know this is only going to give us one triangle, but notice this is 120 degrees. So there's only 60 to divvy up between A and B, but that supports the mathematics because here the B here will be in the first quadrant using the inverse sine function. So we know that B is in the first quadrant based upon this and also based upon the mathematics. So now we're seeing that this triangle is possible. It's not a phony triangle. So now we see B equals the inverse sine, again, exact calculation of 5/2 times the square root of 3/91. So here we need a Google calculus approximation, and then we can actually write now, just before we do that, so now this implies that A equals 180 degrees minus 120. Well, don't put the degrees in the calculation. That's pretty bad. We'll just put it in the answer. Remember, if you're writing degrees in WebAssign and they don't have a little degree symbol by the box, you have to put it there. And if it's wrong, it's because it's reading it as radians. So remember, if there's not a little O by the box and you're putting in degrees, you need to put that degree symbol. Otherwise, you're just writing nonsense. So be careful. I mean, there's no room to be slack, that's for sure. I mean, that's the sad part about mathematics. It holds us to task. And then this will be in degree mode plus inverse sine 5/2 times 3/91 square root. So the thing is that this is an exact calculation here, but if you compute this, you can use this nice decimal approximation in here without any rounding, without having to input this again. That's what I'm talking about. If you're going to use a number that you've computed, keep it nice and proportionate, that is to the mathematics, without any truncation or rounding. So we're ready for this. So let's go to our Google. Now, of course, it's going to have to find it. I don't know. Let me get rid of this. And let's see here. Does it see it? Yeah, let me move this over here. Good, it sees it. There we go. I just have to juggle things around. So now notice, since we want our degrees to be, the conversion to be done for us, we don't want to have to necessarily multiply by 180 over pi. Notice the degree here is highlighted. So we're going to do inverse sine, and then we're going to first input 5 divided by 2, close, times the square root of 3 divided by 91. So we'll say 3 divided by 91, close that square root, and then the inverse sine. And this gives us 26.9955. Now, of course, we could round that to 1 decimal. I mean, just on your paper, not to use in a calculation. And that would, of course, round everything up to 27 degrees. We would never use that in a calculation. And if you do, don't expect your work to be any good. That's just what you put into WebAssign. Now, this is what I was talking about. This gives you a beautiful long digit calculation. Decimals abound for the angle B. So you don't have to input this again. Use this to calculate A. So here's what you can do. Add to this 120 degrees, and then subtract 180. Now this will give you the negative of the angle, which is 33.00449, which you can round to 1 decimal, 33.0 degrees. So that's what I mean by doing exact calculation and not truncating. So when you go back to your calculations, here we do this calculation and we round to put into WebAssign, but then we use this here. So don't truncate or do anything. Use the exact calculation, and then you get a nice answer here, which then you can round. So only round once you have done the exact arithmetic, then round. Now here, if you want, if you're asked to round this to 1 or 2 decimals, do it. Whatever WebAssign says, I don't even know if I wrote that down. I didn't. So that maybe they say 1 decimal for this. Frankly, the idea is if you do your work exactly, then the rounding is trivial. You just use your Google calculator and you're good to go. So nothing about this is unimportant. Why would you bother to do all of this nice work and then round this and use that in your calculation? That makes no sense. So the thing is that in order to affect the WebAssign correctly, you've got to work your text, your mathematics in a way that produces exact arithmetic. And therefore, when you make an approximation, you are approximating an exact value. So there's no round off error built into it. So if you build it in, then you have to pay the consequence with an X instead of a check. So be very careful. This is a beautiful theorem to use, but we have to be careful. Now notice here, all of the arithmetic matches the triangle that we have here. And so we don't have to work as hard. When we're kind of going in this blindly, when we might have an ambiguous case, we have to work a little bit harder. And we have to make sure, okay, are we getting the actual angle in the figure? I mean, by what we have here, we need an obtuse angle. So we need to make a correction? We need to make an adjustment with Professor Ron's lemma. So when you do these problems, the best thing about these triangle theorems is that they make you better at mathematics. You don't necessarily use a lot of these in calculus, but you use the fundamentals that you have to use as you apply these problems. So that's the fundamental reinforcement that makes these problems valuable. Otherwise, I guess we could kind of chunk them. But my philosophy is that by getting you to do this, you'll get better at your trigonometry if you follow the directions. So good for that. Now, what we want to do is look at a couple of instances where we actually think about identities. So I just want to do a couple of examples and then do a calculus substitution trick that you're going to do in calculus 2. So first, I just want to give you some very simple identities. So these are the basic identities, which we already know. So I don't really have to list them. We know them. But they're a group called the cofunction identities that we've only kind of danced around when you did that inverse sine proof, that the inverse sine of x plus the inverse sine of cosine is identically pi over 2. That's a very elegant problem and a very, very beautiful identity, kind of like cosine squared plus sine squared equals 1. But these are called the cofunction identities. Cofunction identities. So this is adding to the basic list. We'll add more as we work through chapter 7. So we have 1, we have cosine. You can use radians or you can use degrees, it doesn't matter. So we're going to look at complementary angles of a right triangle. Cosine of pi over 2 minus x equals sine of x. Now, right now you're thinking, can these be extended modulo 2 pi? Absolutely. And so really, when we think about these in terms of the addition and subtraction formulas, we actually get a more robust feeling for these. But when we think about these, we say we can just always defer to the reference triangle because everything basically finds itself back in the first quadrant with the adjustment of sign. So what you can do here is think of a just basic right triangle of angle X. And then, of course, the complement is right there. The complementary angle is pi over 2 minus x. And then you can call this, hypotenuse. For x, this would be the adjacent side for that angle, and this would be the opposite. So what I'm saying is that this is true, and then you can flip it around. Sine of pi over 2 minus x is also cosine of x. Well, let's just look. These are equivalent, but let's just see why this is true. What about cosine of x? Let's just write it down. Cosine of x is just adjacent over hypotenuse. Well, that was easy enough. And then what if I do sine of pi over 2 minus x? Well, that's just opposite over hypotenuse. So sine of pi over 2 minus x is just the opposite side, which is actually the adjacent side relative to x divided by hypotenuse. So just by looking at the first quadrant triangles, you see that these are actually true. These are regardless of what x is. So these are identities. What's an identity? Equations that are true for all values of the variables for which they are defined. And cosine squared plus sine squared equals 1. That's an identity. I mean, when you say cosine of 50 radians squared plus sine of 50 radians squared equals what? Everybody looks at you and says, I have no idea. Well, the answer is 1. It's an identity. That identity is true for all real numbers. And so you have to kind of take a step back and say, well, every time we write this, we're not specifying what x is. As long as the equation is defined, it's true. So sometimes you just have to think about what you're doing to really appreciate it. So sine, cosine, cofunctions. Let's do another one. Let's start with tangent. Tangent pi over 2 minus x equals cotangent of x. The verification is the same. And then cotangent of pi over 2 minus x equals tangent of x. Tangent, cotangent, cofunctions. And then 3, secant of pi over 2 minus x equals cosecant of x, and cosecant of pi over 2 minus x equals secant x. Secant, cosecant, cofunctions. So maybe we could have introduced these a little bit earlier, but there was no need to. We needed triangles to make this make any sense because this is prior to the addition formulas and subtraction formulas. So if we produce more identities, they better support this. So everything that we produce that's new or looks different, then it must support the arithmetic and the mathematics that we've done before. So we can't just be arbitrary about how we define new items. We have to respect what we've already set up. Okay, so now what we want to do is like, okay, now that we have these new identities, which will be useful in the future, let's just go ahead and prove some identities using basic algebra. So here's an example. When it comes to basic identities, we just write down an equation, and then you can transform one side into the other using the identities that you already know. So we use identities to prove identities. So we want to prove, and here we'll use in some cases we'll use a u as an independent variable, sometimes an x, it doesn't matter. So we have 1 plus tangent squared of u divided by 1 minus tangent squared of u. This is equal to 1 divided by cosine squared of u minus sine squared of u. Now this is an identity. So the proof is what you make of it. So if you want, you should start with one side and transform it into the other side. So let's just start with the left-hand side. It's not unique, and so what I do is not unique. So the left-hand side, just to make this a little bit simpler, I'm just going to write the tangent as sine over cosine with them squared. So this will be 1 plus sine squared u divided by cosine squared u. And then we have 1 minus sine squared u divided by cosine squared u. Now, if we're thinking about using some algebra, we're thinking, okay, well, if we can retire the cosine squared downstairs, we can make it look more like this. So we'll just say, okay, we'll just multiply by a convenient factor of 1, namely cosine squared times cosine squared. And then, of course, distribute. So whatever algebra techniques you want to use, like we would add, subtract A, add, subtract B, add and subtract C, whatever strategies you need, as long as they're legal, are fine. So now, when we multiply, we get cosine squared, and here the cosine squareds absorb, leaving us with sine squared. And then downstairs, the same thing. We have cosine squared times 1. And then the cosine squareds absorb, and we have minus sine squared. But now, of course, the cosine squared plus the sine squared is the fundamental identity. That's just 1. So we have 1 divided by cosine squared minus sine squared. And this is the what? This is the right-hand side. And so we're done. So when it comes to doing an identity, you just practice with these, and the WebAssign will kind of guide you through where you fill in the blanks, so to speak. So you just look at the identity, prove it, and then, you know, basically you can see, well, WebAssign starting with this side, let me just prove it, and then you can go back and fill in the blanks. So the idea is that's a computer algebra way of testing you on an identity proof that will keep you vigilant, like the ones with the brightness and the magnitude of the stars. I thought that was a neat thing when we had the logarithms. So now let's look at another example. Let's say we want to do this particular proof. Let's prove this identity. So example, we have proved that 1 plus sine, you'll like these. This is just using what you already know. They're not tedious, they're kind of fun. You know, you do these in physics when you want to make your formulas look nice. So we have 1 plus sine x divided by 1 minus sine x minus the reciprocal of this, 1 minus sine x. You can make up your own identities too and test your friends. Minus 1 minus sine x divided by 1 plus sine x. And this is equal to the product 4 tangent x secant x. Now, usually when students try to prove identities, they start with the side that allows them to do more algebra. And I tend to agree with that. Usually the more simple side is what the goal is. So when you do an identity proof, you know, if it appeals to you to do some algebra here, you're thinking I could probably move this forward more quickly. And instead of trying to do like a partial fraction decomposition, which is kind of what this is doing. So until you get to that, it's probably better to try the left-hand side, which is going to be easier. So the first thing we want to do if we start with the left-hand side is to say, well, let's just go ahead and get a common denominator. So we have 1 minus sine x times 1 plus sine x. And so now, of course, we need another copy of 1 plus sine x here to balance that. So this gives us 1 plus sine x times itself. And likewise here, we've got to have another copy of 1 minus sine x to balance this. So this is 1 minus sine x quantity squared. So now, all we want to do is expand the binomials. So here we have 1 plus 2 sine x plus sine squared. And then expand the binomial here. So we have a minus. So we have 1 minus 2, sorry, left out the x there, 2 sine x plus sine squared. And then, of course, downstairs, we just have a factor difference of 2 squares. So this is 1 minus sine squared. So we really like the Pythagorean identities. They kind of bail us out of the bad situations. Difference of squares, factoring difference of squares, multiplying by convenient ones. That's really a good way to look at these things. And now we see the 1 minus 1, the 1's absorb, and the sine squared's absorb. But now the 2 sine x's, the minus minus, they add to give us the 4, which we really need. So we have 4 sine x. And then, of course, the 1 minus sine squared is cosine squared. So now equal opportunity. So this will be 4, and we'll just do sine x divided by one of the copies of cosine x, and then a 1 divided by the other copy of the cosine x, just using properties of multiplication. And so now we get the 4, the tangent x, and then by definition, secant x. Oh, and so, sorry, that was a little bit too soon. This is the right-hand side, and we're done. So again, transform one side into the other, and by whatever legal means you can come up with. So this is not a unique process. This is really just practicing good academic exercises. Maybe this is not a very important identity. Some identities we never use, but there are certain identities we use every time we pick up our pen to write mathematics or our pencils. And then you might ask, is the Pythagorean theorem an identity? Well, clearly not. Think about why. I mean, when you think about identities, you think about equations that are true for all values of the variables for which they are defined. And of course, c squared equals a squared plus b squared requires a Pythagorean triple. So the Pythagorean theorem is clearly not an identity, but it would be nice if it were. But if it were, then it wouldn't be much need to do trig, would it? So, you know, we have to pay the price. So now let's do one more before we do an actual trig substitution, which will be kind of an intro to a technique that you're going to use all of this trig in when you take Cal 2. So let's prove that cosine theta divided by 1 minus sine theta equals secant theta plus tangent theta. So remember the difference of squares, the Pythagorean identities, you know, 1 plus tangent squared equals secant squared. All of those are very important and they come up all the time. So never be afraid of using those. So now when we look at this proof, this is going to require, again, I'm going to go with the more complicated side, at least, and use a conjugate technique, which is something we've used before and which you will also use again in the calculus. So let's start with the left-hand side so I can show you this technique. So we'll have cosine theta. So it's going to be a convenient one, but it's going to be a little bit different. The idea here is that this is fairly simple. So we're thinking if we can introduce another difference of squares, we can break up the fraction and get these two terms. So we'll take the conjugate of this. So 1 plus sine theta divided by 1 plus sine theta. Again, this is all based on the fact that these are only true where they are defined. And, you know, that's good. We can live with that. So now just think of your parentheses here. So multiplying cosine by 1 plus sine, that gives us cosine theta plus cosine theta times sine theta. And you're thinking, well, do I need to multiply that? Maybe I'll just end up going backwards. Well, that's okay. I mean, we can do that. No big deal. It's not the end of the world. So now this is just a difference of two squares. So this is 1 minus sine squared. So you're thinking this is going to be really easy. Now, of course, you can see we're going to have a copy of cosine here with the cosine squared, so we can maybe go backwards. Just leave it like that, you know, but that's okay. Sometimes you'll undo things because you'll see that now you can get rid of that particular factor. And it's certainly no crime to do it that way. You're thinking, well, this may be a way I'll break up these fractions and do it that. If I break up the fractions that way, I still get the same answer, but this is just easier. So if you don't want to do it that way, just leave it like it is. This will be cosine squared. So again, this would still absorb that and that, we get the same answer. But now we get what? The cosines absorb. So we get 1 plus sine theta divided by cosine theta. And now, of course, this is just 1 over cosine theta plus sine theta over cosine theta. So if you left it unfactored, then you could just take the ratios here, break up the fractions and get the same answer. And so now by definition, this is secant theta plus tangent theta, which is the right-hand side. So again, these are just fun little algebraic exercises using identities that you already know. So there's nothing new to it. Old hat, so to speak. Now, there's a setup here that I want to talk about. That is, Dr. Stewart is always interested in giving you these glimpses into what you're going to do in calculus. Well, I mean, you don't even need the glimpses, ladies and gentlemen, because if you understand this material, you're going to be fine in the calculus sequence. But there are certain constructs that we will do because we understand the inverse trig functions and their associated triangles. So this is what we do as one technique in calculus, which is called trigonometric substitution. And you're going to learn lots of different techniques of integration in calculus 2 to extend what you learn in calculus 1. And so for a positive a, we might consider the following Pythagorean radicals. That is, we could have an a squared plus an x squared. Sometimes they use u squared, it doesn't matter. And then what we would do is we would think of a trigonometric substitution, which would be a tangent theta. Why is that good? Because we can actually look at this as theta solved in terms of the inverse tangent. And I'll say more about this. this just basically says tangent theta equals x over a. And then we could draw a triangle with this. And then it also says that in this particular case, theta is the inverse tangent of x over a. So that gives us all kinds of information where this would have to live between negative pi over 2 and pi over 2. So I just kind of fleshed that out because I'm going to do an example with that. You can do it for the other two. So here we could have x squared minus a squared. Now this one's not as user friendly. This actually can be improved by using a secant theta. But the secant theta is not as forgiving as the tangent. And so we could say in this case, secant theta equals x over a if and only if theta equals inverse secant of x over a. And so of course, this would be between negative pi over 2 and pi. I said I wasn't going to do it, but I'm doing it anyway. Here, and this would be between 0 and pi over 2 open union open pi over 2 to pi. So this is just basically using our definitions of the inverse secant and inverse tangent. So you're thinking, are these substitutions going to make these radicals simpler? And the answer is yes. So the last one that you'll use with the trig sub will be a squared minus x squared. And the substitution will be x equal a sine theta. So equivalently, this will make a triangle. Sine theta will be x over a, again, opposite over hypotenuse. Here, this is hypotenuse over adjacent. This is opposite over adjacent. So if and only if theta equals inverse sine of x over a, and we know this lives between negative pi over 2 and pi over 2. So when it comes to trigonometric substitutions, these are all based on just what I've taught you in trigonometry. You could already set up these integrals. You wouldn't know the differentials and you wouldn't know the antiderivative very well, but you would certainly understand the trigonometry here. So let's just look at an example here. This is something. Here's an example that Dr. Stewart gives you, and I'm going to first write the actual expression that we want to transform, and then I'm going to put it in an integral. So if we had 4 plus x squared here, then you'd look up here and say, okay, well, the a squared is 4 squared, is 4. So a is what? 2, the square root of 4. So this would say use x equal 2 tangent theta. So we compare here, the a squared is 4, so a is 2. So that's going to transform this, but why would you be interested in this? Well, when you take calculus, you'll take the differential, and that'll be 2 secant squared d theta. And then you'll substitute all of this doing what they call a miscellaneous transformation. And that's going to produce a trig integral. So basically what you're going to have is the integral of x squared square root 4 plus x squared evaluated relative to x. And you're seeing that this is just the algebraic part and the dx is just in the place of the 1. So it's like, okay, this is called the indefinite integral. This is called the integrand. And so in order to do this, you can either use an integral table, which was based on this substitution technique, or do it directly yourself. So if you find yourself in like a calculus 2 class and you look at this integral, the first thing you're going to say, well, you know, I know these substitutions, let me transform the integrand. So you can do the little side calculations first and then fit them back in just to kind of keep everything nice and neat. So first, let's look at the x squared and see what we get. Let's just do it piecemeal. There are many ways to do this. You can do this linearly, or you can do it piece by piece and then just put it together. So x squared will be what? Now remember, up here, theta lives between negative pi over 2 and pi over 2 for this particular substitution. Secant is not as friendly to us. We get two branches, and so you have to be very careful with it when you're doing definite integrals. So x squared would be 2 tangent theta squared. Well, that's easy. That's just going to be 4 tangent squared theta. So that's what the x squared looks like. And now let's look at the radical. So we'll just do the 1/2. So 4 plus x squared to the 1/2 will just be 4 plus, well, now we know what x squared is. Let's just go ahead and fit it in. That's 4 tangent squared theta to the 1/2. So now when we look at this, this is just like doing the law of cosines. We can factor this and clean it up. So this will get, and now you see why do we make this substitution? Because it simplifies the radical. So this will be 4 times 1 plus tangent squared. But now, of course, we got the product, the square root of the product. Here, the square root of 4 is 2. And then 1 plus tangent squared is the Pythagorean identity. That's secant squared. So we get the square root of secant squared. So now, secant squared square root is the absolute value of secant by definition. But now we're okay because for these particular intervals, this is in the fourth quadrant and the first quadrant where the x value, cosine secant, are positive. So we can remove the absolute values and we have one sign, just the positive sign. So we get 2 secant theta. So now what we see is, and you're thinking, well, wouldn't we have to know about integrals of trig functions? And that's why before you would do this, you would do what they call trigonometric integrals, using the calculus of the trig functions and their backwards formulas. And so you get beat over the head with the Pythagorean identities to rewrite things, to write things in standard form, as I call it, table ready. Once the integral is table ready, boom, you can hit it with the integral formula and you're done. So the idea is that you will do some work before you get to this part, but now notice all of the ingredients are here. So when you write the integral, this implies that the integral dx over x squared times the square root of 4 plus x squared will now equal, just fill everything in, dx is 2 secant squared theta d theta, x squared is 4 tangent squared, and we're going to have a 2 there, so 4 tangent squared times the radical is 2 secant. So we get this integral. So we get 2 secant squared theta divided by 8 tangent squared theta secant theta. And then when you look at this, you're thinking, okay, well, one of the secants will go away, and then that'll just be a 1/4. So this gives us secant theta divided by 4 tangent squared. Oh, I left my d theta, sorry. D theta tangent squared theta. And then you would use the Pythagorean identity on this, and boom. So this is, well, we can go one more step. Well, let's just do it. This is just, I'm not doing any calculus. I'm just doing algebra, which you know how to do. So this will be secant theta d theta. Tangent squared is just what? Secant squared minus 1. We've got a 4 there. So when you break this up, you're going to get 1/4. The 4 can factor, and you're going to get 1 over secant theta minus secant theta d theta. And I'll teach you how to do those integrals. So all of this stuff right here, except for that, all you do is just fill this in and do the algebra. When you get to the tangent squared, you use the Pythagorean identity, and these are 2 integrals that you can easily do. So basically, the trig substitution, you know how to do right now. You just basically use that to make this so simple that you can knock a home run, so to speak. So the idea, why is trig important? Well, you got to know the calculus of the trig. And then, of course, when you get to this part, this is just all trig. So to say that trig's not important is to just not be honest. Trigonometry is central to doing calculus, and without it, it's really a nightmare. So what I wanted to do today was kind of get a little bit off the beaten path and just have a good time looking at some neat formulas, doing some extra algebra, and showing you how this trigonometry is actually going to help you when you get to the calculus class. And so before you do all of this, you're going to learn about limits of sines and cosines. You're going to learn about derivatives of sines and cosines and Riemann integrals of sines and cosines. And then once you get done with all of that, you're going to start into calculus 2 using applications of the definite integrals, then start working on these integration techniques. So this will be in the 2nd semester of calculus. So if you don't learn this now, by the time you get to Cal 2, all of this will be dust. So that's what I'm saying. You don't use all of this every day. You use it when you have to use it. And that might not be at the most opportune time. So hopefully you've enjoyed this little excursion into triangles and law of cosines and trig subs. Again, the test will cover through 6.4. I won't include the law of sines, since that's kind of like the law of cosines. I'll just give you a little break there, and same time setup and all that. So good luck with that. And once you finish that, get cracking on this stuff, and I'll put up some new sections for chapter 7, and we'll be on our way to finishing this course. We still have a lot to go, but that's okay. Everybody have a great day. Thank you for your attendance.
You too. Thank you.
Bye.
Bye. Thank you.
You have a good day. I know you're looking forward to calculus. It'll be easier than this class.